Why does the current in the secondary winding increase when the voltage decreases? Yep, it's basically what you guys are saying. So because the transformers transfer nearly constant apparent power, or VA, when voltages step down, current must rise proportionally to maintain. So V primary, I primary total is equal to voltage secondary, current secondary. Yeah, so basically power in, power out. There is always going to be a little bit of loss, so we can't say it is a perfect and true representation of the input to the output. Cool. So why do we laminate the steel core on a transformer? You guys are mostly on the right track. So we do it to reduce the eddy current losses and the heat generation because of those currents, improving the efficiency and performance. So by decreasing the surface area or the cross-sectional area, it's less about surface area and cross-sectional area. If we think about our cable sizes, the more cross-sectional area, or for example, 16 mil squared versus 6 mil squared, the 16 mil has less resistance versus the 6 mil. So if we have a smaller cross-sectional area, we increase the resistance. So if we increase resistance, we reduce the current because the voltage, well, for realistically, the voltage won't change. But if we increase resistance, we decrease current because resistance and current are inversely proportional. So it's because we increase resistance. And why do we use silicon steel? So why do we use silicon steel instead of just ordinary iron? No, nothing to do with hydroscopic. Hysteresis. Yep, it has less reluctance, or it is what we consider magnetically soft. So magnetically soft means it is easier for us to magnetize it versus regular steel. So the silicon isn't the insulation. It's more of we infuse the steel with silicon. Okay. Cool. So transformer. That's surprising. Cool. So we have a transformer and it has a turns ratio of 12:5 and a primary voltage of 240. What is our secondary voltage? Now we've got a couple 48s and a few 100s. Okay, so to figure this one out, we know that the number of turns in the primary divided by secondary is equal to the voltage primary divided by secondary. So if we punch in the numbers, 12 divided by 5 and 230 divided by the voltage secondary. So therefore 2.4 equals 230 divided by the secondary voltage. So we can transpose this to be the voltage secondary is the same as 230 divided by 2.4, which gives us 95.83 volts. So that's how we would go about working this problem out. So we can do the cross multiply, but it is easier to just take 2.4 and divide 230 by 2.4, because that is our turns ratio. So if it was the opposite and we had a that is a good point. Yeah. Sorry. Someone didn't read the PowerPoint they were making. I wonder who that was. Yeah, so if we're using 240, it would be 100. Yeah. There we go. Yeah, you guys are right with your 100 volts. I literally copied and pasted from the lesson plan they gave me and did not read it too closely. My bad, guys. Cool. So we'll move on to talk about the features and applications of the types of transformers that we have out in the world. So far we've focused on how the transformers work, magnetic induction, turns ratios, and current relationships. So now we'll look at those designs actually do out in the field, where we use them, what their limitations are, and why one type might be chosen over another. So the different types of transformers you might come across. So your standard double wound. So this is the most common type of transformer that most electricians will come across, simply because we use them more often for our our drivers, for our downlights, and all kinds of stuff like that. The auto transformers, most of the time you won't see auto transformers out in the world unless you're working in kind of like a test bench scenario, just because we don't really need to change the voltage with a variac. And most of the time, auto transformers aren't considered all that safe to be used in day to day. Then we have our isolating transformers. So these are used for separating us from voltage. It's the kind of thing we would use in a damped situation, pairing that with a step-down transformer to make separated extra low voltage, or our SELV. And remember, that's what it means, separated, not safety. There's a couple contradictory terms out there, but it is separated because we separate the earth of the load from the supply. Yep. Then we have our instrument transformers. So these are the things that are connected. So this looks like, yep, that's a potential transformer. So when I say potential transformer, what am I talking about when I say potential transformer? What you guys have read so far in the learning resource, what is a potential transformer? Has anyone got any idea what I'm talking about when I say potential transformer? Yep. So it's used for protection monitoring, step down HV. Yep. But what is its purpose? Okay, cool. Sweet. So we've got potential transformer and we've got current transformers or CTs. So they are kind of the same thing, but they're used either in conjunction or to measure separate things. So a potential transformer, so when we talk about potential difference or electrical potential, we're talking about monitoring voltage. So a potential transformer is used for measuring voltage, whereas a CT or current transformer is used for measuring current. Yeah. So we'll go over that a little bit more later in the lesson when we talk about the instrument type transformers. Cool. So the first we'll talk about is your standard double wound transformer. So they have a few key features throughout the double wound. Just look at my notes on. But remember, every transformer works on the same fundamental principle. Two or more windings linked magnetically. The way those windings are connected and insulated gives each type its specific features and applications. So the double wound, so key features. So we have two completely separate windings, our primary and our secondary. So there is no electrical connection between these two windings. They are electrically separate. Okay. And remember when we talked about it talks about provides galvanic isolation between the supply and load. So when we talk about galvanic isolation, galvanic cells, there is no possible chance of any physical leakage between each of the windings. It can be used to step the voltage up or down depending on the turns ratio. So specifically for a double wound, we're just talking about a double wound. We're usually talking about a step up or down transformer because it's not an isolating transformer. So yeah, it's used to step up and down depending on the turns ratio. And these are used from anywhere from the HV lines all the way down to our transformers for our microwave ovens. They typically have a laminated iron core, which is resin or varnish insulated. So normally the wire is resin or varnish coated wire, which makes it electrically separate, but still allows that magnetic field to permeate between the two. Cool. So the applications, so mains voltage conversion, so 230 to 115 for our imported equipment, or our mains conversions from low voltage to high voltage and high voltage to low voltage. We use them for control circuits and lighting transformers. So has anyone heard of what we call a dichroic lamp or a dichroic light fitting? They usually come with a little transformer that we call a pinky. Not quite neons, no. So what it is, it normally came with a little pink transformer, and you had small leads to a little kind of ceramic holder, and you'd plug it in, and it had two metal pins on the back. So the dichroic lights are actually AC. They run on 24 volts AC. So instead of having a 230 to 12 volt DC conversion, we just have a straight 230 to 24 volt. So it's just a standard. All good, Jack. Just join in and then watch the video again. Yeah, so halogen style light. Yeah. And so we also use them for control circuits. So a lot of control circuitry runs on 24 volt DC. So we need the transformers to step down the voltage to our 24 volt DC, sorry, AC. Cool. We use them for power supplies for our electronics or tools requiring electrical separation. So they can be used as an isolating transformer, but also power supplies for our electronic devices, like our computers with the built-in power supplies. Cool. So some advantages of our double wounds. So full isolation improves safety and noise immunity. So we don't get as much of the noise transfer from the main line into our electronics. It simplifies earthing and protective device coordination. So the earthing requirements aren't as stringent if we're at lower voltages. But some limitations. So it's bulkier and costlier than an auto transformer. So the size and weight can be a factor. If anyone's ever picked up a double wound transformer, even the ones in the microwaves are still pretty hefty. The main weight inside of a microwave is actually the transformer. So the efficiency is slightly lower due to the extra windings and losses, i.e. if you have more windings, you'll have more heat, so you'll have more heat losses. And obviously the iron core needs to be bigger or the steel core needs to be bigger to accommodate the extra windings. So that's more weight and more hysteresis loss because of eddy currents. So where in your own experience might isolation between input and output be especially important? Where have you guys had to use the transformers because they will isolate the supply? Damp situations, yeah. Yeah, you definitely want to keep the 220 to 110 completely separate. Sometimes we do use them a lot and we forget about it. So if any of you guys have done garden lighting, you use a transformer. Yeah, drivers, 230 to 24 volts, your standard drivers, yep. There's a double wound inside those. Right. Cool. So auto transformers. The things we cannot use for children's toys because of the possible dangers associated with them. Cool. So some key features. So it has a single winding shared by both primary and secondary. So part of the coil serves both. So if we have a single winding and we're going in a step down configuration, the winding will be tapped on this for the secondary side partway down the coil. But if we're doing a step up, the input or the 230 volt side or the line side is tapped halfway. So we need to remember if we're doing our drawings and we have a winding, we need to make sure if it's a step up, we tap the winding halfway for the input. And if it's a step down, we tap it halfway or whatever way we need, point we need to for the load side. We need to keep an eye on whether the question is asking us for a step up or a step down auto transformer, and make sure we put the correct, the tap in the correct side, depending on whether it's step up or step down. Cool. So there is no electrical isolation between input and output. Because they share the same winding, we can't have separation or isolation. They're compact and efficient due to fewer windings. So less copper means less copper losses, less iron means less iron losses. So just overall, we have less losses, but we know we sacrifice our efficiency, our electrical isolation for efficiency. Cool. So some of the applications for our auto transformers. So small voltage adjustments, so 230 to 115 or 240 to 110. Or if we have potential voltage differences on the input, because obviously depending on where you are, as soon as 8 o'clock comes around, all of a sudden the load picks up and the taps change on the transformer. And depending on where you are in the supply chain, your voltage might drop or it might increase. I was doing moving or relocating a socket outlet at my house yesterday, and I was getting 243 volts at the socket outlet. So that's not meant to get that high, but at the same time, I was only using my T5 to take the measurement. So T5s, they're a good indicator, but I would not trust them to be accurate with their measurements. They will tell you whether you're getting about 230, but they will not give you accurate voltage readings. So it could have only been 240, but again, it's still higher than what I'm supposed to be getting. So obviously, if that's too high for certain equipment, we need to be able to adjust it as need be. So variable output devices like Variac. So when you guys actually know stages 2, you don't do any work with transformers. So eventually you will do some transformer work on your block course. And one of the transformers we use is a Variac. That is our auto transformer. They're the only auto transformer that I know you can buy out there through hobby places like Jaycar. It's basically used as a variable power supply. Cool. And we can use them for motor starting, so reduced voltage starters. CB time, so circuit breaker timing. Is that where you, for the big network circuit breakers? Okay, cool. Yeah, so we can also use them to reduce the voltage for motor starting. Because remember, if we reduce the voltage, we reduce the current. So we can use auto transformers for that as well. Cool. So thinking back to how we had motors, when we talked about motors before, if we took a motor from America and we reduced the voltage on it with a Variac down to their standard 220 for a two-phase motor, or a 110 for the single-phase motor, would we get the same speed that we're supposed to at 110 volts on our supply network? Just going back to motors to see if anyone remembers whether we would get the same speed if we powered a US motor on our supply network through a 230 to 110 transformer. Yep, cool, sweet, straight away someone gets it, yeah. So yeah, a lot of people think, oh, I can use the transformer to step the voltage down and make my piece of equipment. So for example, a tutor I had when I was doing my apprenticeship, his wife was American. She brought over her like classic KitchenAid, very expensive piece of kit, especially the American made ones because they're all cast iron, like old KitchenAid. And so they wanted to get it to work here in New Zealand, but obviously, even if they used a step down transformer, they could never get it to spin the correct speed. So they had two options: either buy a really fancy device to do the work, like an auto transformer, or rectify it to DC and then use a inverter, or replace the motor inside the mixer. I'm not sure what they did. I haven't seen them since. I have to find out about that. The American frequency is 60 hertz. Yeah, so the Americans run on 60 hertz, whereas we run on 50. That's why most monitors. Why is everywhere different? Because no one could agree. Just like Americans are a bit obstinate with the imperial versus metric system, or as they like to call the standard system. Yeah, so when so Europe uses a similar voltage to what we do, but the reason they used a higher voltage in Europe was you could use less copper to do the same job when they increased the voltage. Whereas America decided, no, lower voltage is safer. We're going to use bigger wire. So the other way they get around that is if you ever go over to America and look at the wiring they use for standard house wiring, it's all solid stranded for the most part. Their wiring they use for their power points and lighting, it's all solid strand, no individual cores. Yeah, but it's not like 1 mil. So if you think about if 2.5 was solid core, that's what they use for their lighting. If 4 mil was solid core, they use that for their PowerPoints. So that's what they do. Which, to be fair, it means it's less resistance because there's no air gaps between the cores of the conductors. Obviously, when they get to mains cable, they do use stranded. But yeah, for the stuff that's standard in-house, they use solid core. So yeah, that's their style. Cool. So the advantages of using an auto transformer. Well, obviously they're smaller, lighter, and cheaper and more efficient. And that's probably about the only advantage of an auto transformer is they're small, light, and cheap. And we get better efficiency out of them. The limitations or the safety notes. So we have no isolation. So earth faults or surges can transfer directly to the load. So it cannot be used in circuits requiring separated or safe extra low voltage supplies. So again, separated, not safe. Yeah, so if an auto transformer has no isolation, what hazards could you cause in a damp or workshop environment? So if an auto transformer has no isolation, what hazards could that cause in a damp or workshop environment? Yeah, we could get full line voltage on the output. Earth fault, yeah. It's also known that, yeah, shock. So you could get things like touch voltages where the voltage rises to a point, especially if it leaks to earth. You could also, if it's a step up transformer, you could have full, not the full line voltage, but the full secondary voltage at the primary side. So if you're going from 230 to a higher voltage, all of a sudden you might have the higher voltage present on the input, depending on the type of fault that happens. So the key features of an isolating transformer. We're moving on to isolating transformers now. So It's a double wound, but it has extra insulation and separation between the windings. They're designed for electrical isolation rather than voltage change. So they often have a 1-to-1 or a 1-to-1.13, a very, very small difference, and provides a floating secondary circuit with no reference to earth unless bonded locally. So floating circuit basically means it has no connection to earth, is what we're saying by that statement. So the reason we may not often have a pure 1-to-1 ratio is because when we plug in a load, the volt drop inside the transformer and the load, because the load is in series with the windings, the volt drop across the secondary may cause enough of a volt drop that the voltage becomes too low, especially if our supply voltage is low. So I think I've asked before and no one's had the use of or installed a isolating transformer before. Is that still the case? Anyone had to use an isolating transformer or installed one? Yeah, Ethan, when did you use/install one? Every control room in a substation has one? Oh, yeah. Oh, okay. It's powering a whole garage. Yeah, pretty big isolating transformer. Ah, interesting. Heat sprayer for cow sheds. See, I never would have known that unless I taught this class. Cool. See, we all have different experiences. I've only ever installed one, and it was for the operating theatre in a hospital for the cardiac area. But again, I just put it in the ceiling and hooked a couple wires to it. There wasn't a whole lot to do other than the fact it was effing heavy. Cool. So some applications for our isolating transformer. So maintenance and testing circuits. So sometimes we need to have a separate earth for maintenance and testing purposes. Cool. So medical equipment, laboratories, and damp area power tools. So again, medical equipment, if there's a chance that it may shock a patient to earth, this is especially important in hospitals, especially because some patients may have undergone heart surgery, and so their hearts are weak, and so cannot take even the smallest amount of shock across their heart. Laboratories. So if a lab is going to have maybe potentially an explosive atmosphere or explosive chemicals, we don't want the possibility of them having a shock through the steel bench to earth or through us to earth, especially because it'll decrease the risk of spark. And obviously damp area power tools were separated from earth. Even if the earth is wet, we can't get a shock through the tool earth back to the supply. And so portable isolation units, 230 to 230 volts, also known as the shoebox transformer, used for damp area power tools, and where the other possible use is for mining. They do use them for mining situations, especially when they're dealing with explosives or the use of explosives, because obviously we want as little possibility of a spark occurring as possible. Cool. So some advantages to our isolating transformers. So maximum shock protection. So if there's no earth reference on the secondary, we have no return path. So we cannot get shocked through ourselves through the earth. We can get a shock phase to neutral, but we cannot get a phase earth or neutral earth shock. Cool. It reduces electrical noise and earth loop interference. So on particular medical equipment or so going back to the laboratories, testing equipment, Sometimes there's a bit of noise on the earth. Has anyone ever done any work with kind of audio stuff or music stuff? So have you guys have done it, have you had any like buzzing on the ground loop, which causes, a little bit of noise and feedback? So what you can do is you can use a box called a ground lift box, which basically does the same thing, uses a transformer to separate the signal from ground, meaning that you don't get that noise. It's really common on live audio gear that they use isolating transformers, not for electrical, but for signal. And a lot of the music gear will be powered by power supplies that have a isolating type transformer, or at least a transformer. That way we reduce the noise on the live sound. Same for some theatre lighting as well. So that's another application for our isolating transformers. So the limitations, so we're limited to a single appliance or controlled circuit. And we must not have secondary earth unless bonding between connected devices is intentional and local. So why do we usually connect only one appliance per isolating transformer? So why would we only want to use one device or circuit per isolating transformer? Yeah, so basically, if we have two appliances and for some reason, we have two devices plugged in and they both get phase to frame faults, there is a potential for current to flow between us through the earth to the other appliance, unless we bond them. If we bond them together, then it will create a dead short and blow the fuse protection on the transformer. Yeah. If we're going to use multiple appliances together, we need to bond them together. Why might we need to use two appliances from a single isolating transformer? Can anyone give me a reason why we might need to use two devices from a single isolating transformer? Calibration, possibly. Anyone think of any others? Yeah. Or the devices are designed to work together. So for example, when you plug the vacuum cleaner into the isolating transformer, and then you plug the tool that you're using that's connected to the vacuum cleaner to the vacuum cleaner. So if they're equipment that's designed to work together and you have to plug them in at the same time, that is the best case scenario for using one isolating transformer. So more often than not, if they're designed to work that way, they will be purpose built like that. But again, it's a very rare occurrence that that's going to happen. Yeah, I've only heard of it once, and it was like a one-off machine that was used to do one job, and it was in a basement that was below the water line, and they were working on waterproofing it. I think it was a vacuum and a core drill, and they couldn't get the pneumatic one in. So that's the only time I've heard of it used. It was the core drill, and it was, I think, a water pump that was designed to work with the core drill. Yeah. Cool. So remember, all three share the same magnetic principle. They all use the same magnetic principle, but their design defines how and where they can be used. So isolating is the big differentiator. When safety is critical, isolation wins every time. So when safety is number one, we're going to throw the auto transformer out the window. Goes through with anything. Safety is the number one thing. If it's not safe, it's not worth using. Cool. So before we move on, anyone got any questions about anything we've covered so far? Okay, cool. If anything comes to mind, just throw it into the chat, or if you want to turn on your microphone, turn on your microphone, all good. But yeah, just let me know if you have anything you want me to quickly cover or questions to answer. Cool. So restrictions and safety considerations. So transformers are robust and reliable, but they are not indestructible, as we've seen in the past few days. Every transformer has operating limits: electrical, thermal, and environmental, that we need to respect to keep them safe and performing correctly. So we'll take a look at what those limits are and how to recognize them. So first, we have our thermal and load limitations. So think of your transformer like a radiator. It can only get so hot before something starts to fail. Even a small overload might seem harmless short term, but the temperature rise can quietly destroy the insulation over time. So every transformer has a VA rating that defines how much apparent power it can safely handle. Exceeding this rating causes excess heat in the windings and the core. So heat's our biggest enemy. Prolonged overloading degrades insulation and shortens life. There's only so much heat that a transformer can safely dissipate, and this is what our VA rating reflects. So each transformer has a temperature rise limit. So for example, 55, 75, 105 degrees C, and it's based on its insulation class. So A, B, F, and H. They talk about this, but then they don't give me them. Okay, cool. So copper loss or I squared R and iron losses can both contribute to heating. Overheating accelerates insulation breakdown, leading to short circuits or open windings. Cool. So the insulation class. So class A is 55 degrees, B is 80 degrees C, F is 115, N, they even have N as 130 and H is 150. Obviously, if you guys out there in the field who deal with the transformers a lot more, please feel free to correct me. But yeah, we need to make sure we don't exceed our VA rating because that is basically the maximum amount of power or heat that the transformer is rated to expend. Now, some would say, oh, it's all good to push it over just a little bit for a short period of time. But if we keep doing that, eventually the transformer is going to catch on fire. The H temp rating. (150°C). It really depends on where you are in the world. Because obviously the environmental factors have different things. So yeah, for us in New Zealand, 180 is H. Cool. So now we're going to have a little fun exercise. Find the VA rating on the nameplate. So I will give you guys a transformer nameplate, and then I want you to give me the VA or kVA rating of the transformer. Here's the first one. It should do, but remember the fuses are HRC fuses. So they're not designed to trip within 4 hours at 1.5 times its rated current. So the fuses can allow 1.5 times the rated current for up to 4 hours. Yeah, always make sure you put the correct unit. So for this one, yeah, 1250 kVA. So 1,250,000. So it's 1,250,000 volt amps. So a pretty beefy transformer. Cool. What about this one? Cool. But yeah, you all got there in the end. Yeah. So here on the nameplate, we have a rating of 10 kVA. Cool. What about this lovely specimen? Yep, crude as it is. It's been written in some kind of marker there, obviously because it's rubbed off over time. But yeah, 300 kVA. Cool. And lucky last, There are some things in English on it. You guys have found the voltage. So I don't expect you guys to, yeah, so this is the VA plate down here. So this type of transformer is actually variable in its VA depending on its configuration. So obviously you're not likely to come across a Japanese transformer in New Zealand, but it's good to be able to identify certain things. So I can see the VA here, and I'm guessing it is in MVA or KVA. Yeah. Yeah, on a line tap changer, yeah. Yeah, no, you will not come across anything like this. Sorry, it was just kind of me having a bit of fun. I did find one that was in Russian, but I couldn't even find the VA on the nameplate, so I decided not to use that one. Cool. So we'll move on from the nameplate. So core saturation and over voltage. So when the magnetic core reaches its saturation point, it can't carry any more magnetic flux. So the transformer draws excessive magnetizing current, causing heat and distortion of the output waveform. It's usually caused by overvoltage on the primary or operation outside its design frequency. So 60 hertz transformer on a 50 hertz supply. So what might happen if a 230 volt transformer is accidentally connected to 400 volts? It is, yeah. So basically, the core will saturate too quickly, basically instantly, because it's being exposed to a higher voltage than it's supposed to. It will draw a huge current and cause overheating or failure. Because it's reached saturation point and we're trying to saturate it even more, it'll draw excess current to do that. Those key safety notes. Always verify your voltage before you energize a transformer. So make sure it is rated for the voltage you're about to put it on. If the transformer hums loudly or overheats quickly, it's a red flag for saturation or incorrect voltage or frequency. So you plug it in and it hums louder than you think it should, disconnect it straight away. Check your voltage, check you haven't accidentally connected the secondary to the primary, or you're connecting a 400 volt to a 230 volt, because the last thing you want to do is oversaturate. Cool. So cooling, ventilation, and location. So just like people, transformers overheat faster in stuffy rooms. So good ventilation isn't optional. It's part of the safety and design. So transformers rely on airflow or oil immersion to remove the heat that's generated due to the current flow and magnetizing effects. So the enclosures must allow adequate ventilation, and we must avoid covering vents or placing units in enclosed cabinets. So one of the linesmen who came down for a block course once kept telling me about how obviously the transformer cabinets, the vents they have, they get quite warm in winter. So obviously, because we're trying to heat our homes, the transformers heat up. And so obviously those who sleep rough end up sleeping in front of the transformer vents, which can cause issues. Ambient temperatures also affect performance. D rating may be required above 40 degrees C ambient temperature. So oil fill types must remain upright to ensure cooling and insulation oil circulates properly. So if it's on its side, the circulation isn't going to work. If it's upside down, it might, but I think it's pretty obvious if you put the transformer upside down. Am I wrong in saying that, Daniel and the guys? It's pretty obvious if the transformer's upside down. So yeah, obviously, ambient temperature. Yeah. Yeah, if the lifting eyes are on top, it'd be pretty difficult, but I've met some motivated idiots. Oh, did I say that out loud? Yeah, so ambient temperature. This is a big thing. Obviously, with climate change, the ambient temperatures are changing quite a bit. So obviously in summer, it's getting quite hot in certain parts of the country. If you're in the sun, it gets really friggin' hot. And obviously because it's so hot, we're still running our air conditioning units. So that can affect the transformer's performance. And obviously this will degrade the transformer over time, thus leading to more transformer issues. Cool. So cooling, ventilation, and location. So we need proper isolation and earthing to ensure fault protection and reduce the risk of electric shocks. So transformer frames and closures and all cores must be earthed. So secondary circuits should be earthed or bonded only where appropriate. So TN systems or local equipotential bonding. Avoid creating multiple earth references, which can cause circulating currents or noise. And just as a safety note, always isolate and discharge before testing or maintenance. Residual magnetism can induce unexpected voltages. So we must make sure we earth and bond our metal frame and our transformer star points correctly. But we need to make sure if we disconnect the transformer, we isolate and discharge the transformer, because magnetism inside those things is pretty strong and it will keep creating residual voltages and for a while until it's shorted out on one side. Cool. Physical and environmental protection. So ingress protection is a big thing, or IP ratings. It indicates the suitability for damp or dusty environments. So obviously not all transformers are allowed to be anywhere near water. Obviously, if it's an open type, we need to keep it away from the water because we don't want water getting into the actual wiring itself. But if it's a sealed unit, that's another story. So for outdoor and industrial use, we need to ensure our enclosures, if it's not already in one when we buy it, meet at least IP54 or higher. And obviously, depending on the zones, we need to increase that minimum rating. And we need to make sure we protect against vibration and mechanical shock. These can loosen the windings or the terminals and can shake apart our connections. And we need to ensure the protected devices, our fuses and our breakers, match the transformer's current rating. So where would you mount a control transformer? On the floor or on an elevated on a panel? And why? What other reasons might we have? Panel, greater airflow, yep. Are you saying, yeah, Andy, damage, but are you putting it on the ground or on a panel? If we're talking about big transformers, yep, definitely put it on the ground. But if we're talking about a control transformer, so we're talking about a transformer for control circuitry. So it's probably only, it would fit in your hand. Yep, keep it away from people, especially fingers, yep. Yeah, so the best place for a control transformer is to get it up off the ground, away from people, to allow good airflow, and it's more easily accessible for maintenance, and it's better for moisture protection because who knows if the ground's going to get wet or not, without being given other factors like is it inside, is it outside, is it under a deck, what is it supplying. We don't know 100% what the correct answer should be. Obviously, if we're talking about a big transformer, it's going to be better to keep it on the ground because otherwise we're going to have to build a huge mega platform for it. Cool. So every transformer is designed for a specific set of conditions. Respect those limits, voltage, current, temperature, and environment, and it will run quietly for decades. Ignore them, and we'll be replacing burnt insulation before you know it. So, what happens if a transformer runs beyond its VA rating for too long? Yeah, so the bare minimum is going to heat up and it's going to damage the winding of the insulation. So the bare minimum that's going to happen, and yet worst case scenario, it's going to get too hot, and then it's a fire risk, especially a potentially big fire, especially if it's a oil-filled one. Cool. Why does overvoltage cause core saturation? Yeah, it's above the design limitations, but why does that cause core saturation? It's not got anything to do with heat. Yep, so basically it comes down to we put more voltage, we created more magnetic flux. So it's not about the EMF so much as about the resultant magnetic flux. If we increase, we create too much magnetic flux in the iron core after we've already saturated it, it's going to draw excess current to compensate. We're going to have more magnetic eddy currents inside the core. So if we saturate the core too much with our magnetic field, then it draws excess current inside the core itself. Yeah. The magnetic flux is proportional to the amount of voltage we put in. So we put too much voltage, we create too much magnetic flux, which overheats the iron core. Cool. So what's one reason it's dangerous to block airflow around the transformer? Yeah, basically by blocking off the ventilation, we're blocking off one way for it to dissipate heat. And a hot transformer is an unhappy transformer. Cool. So some key points to get down before we move on from this part. So overloading and poor ventilation lead to overheating and insulation failure. Core saturation from overvoltage or wrong frequency causes high current draw. And correct earthing, ventilation, and IP selection ensure safe operation. And we must always observe nameplate data and installation standards for long service life. So make sure you at least take a note of these before we move on to the next section. And if anyone's got any questions, we'll deal with those before we move on. Cool. No one's got any questions? Is anyone not ready for me to move on? Sweet. Sweet. So isolating transformers. So you've already seen that isolation is one of the key benefits of certain transformer designs. Now we'll look more closely at isolating transformers themselves, how they work, why we use them, and what makes them so effective for electrical safety. So unlike auto transformers, we have no shared winding here. The two circuits are magnetically linked, but electrically separated. That's what makes isolation so valuable. So we can say they are magnetically coupled, but electrically isolated. As you can see, the guy is getting a shock, but there is no return path to Earth because the secondary output of the transformer is not connected to Earth. Cool. So operating principle. So the transformer has two windings, primary, secondary, wound on a common magnetic core. Turns ratio is usually 1:1, meaning secondary voltage equals the supply voltage. Sometimes it's changed to a 1 to 1.05 or something like that to account for the volt drop across the windings. Cool. Energy transfers magnetically, not electrically. The secondary is floating. It has no direct connection to Earth or supply neutral unless one is deliberately made. So the result, a fault on the secondary circuit does not create a return path through the Earth. So fault current cannot flow under these normal conditions. So if someone accidentally contacts one conductor on the secondary side, current has nowhere to go. There's no circuit back through Earth. That's the key safety advantage. So by isolating ourselves from the supply, we have no return path. We cannot complete the circuit between us and the supply, unless for some reason we touch an appliance that is earthed. So if we're using an appliance connected to an isolating transformer, we must make sure that we do not then use an appliance that is connected to the supply, because that can possibly create a return path. Cool. So the benefit, so we get protection against earth fault, no reference to Earth, no path for shock. We have reduced touch voltage risk, so a single fault on the secondary will not produce a dangerous potential difference. Improved noise immunity, so no direct electrical connection, less interference and harm in sensitive circuits, which is very, very important for any kind of monitoring or measurement circuit or audio work or visual like recording. So safer maintenance testing. So circuits under test are separated from the supply, protecting both the user and the instruments. So in what type of work environments would these advantages be valuable? So in what type of work environments would these advantages be most valuable? Medical areas, yep. Hospitals, for sure. Schools, yep. Hospitals and labs, yep. Laboratories, yep. Rest homes, yep. Yeah, also potentially your workshops and your construction sites, because obviously we need to protect. So obviously if we're working in damp areas or we've got equipment that we need to work on, it's a lot safer to work on it if it's isolated from the supply. So some typical applications. We've got portable tool transformers on construction sites. So 230, 230 volt for drills, grinders, and test gear, or any gear that might be working in an environment that is not safe to have any kind of spark. Service and testing benches, so it isolates the technicians from the mains when working on live equipment. So sometimes we need to work on live equipment to see how it performs as it's operating. Medical and laboratory installation, so patient and operator safety from shock. Audio and electronic systems, so isolation reduces the hum and the electrical interference. So they're used anywhere the risk of electric shock or interference needs to be kept to an absolute minimum. So sometimes you'll also find them in data centers because we need to eliminate the noise from the supply network. Cool. So safety rules and restrictions. So although isolation transformers enhance safety, they must be used correctly. So please note, this might come in handy for your assessment. So 1 appliance per transformer. Connecting multiple loads can create fault paths between the appliances. Test tag facilities might use them, but they also can use portable appliance test equipment, which do live testing as well. Yeah. So we can connect, do not connect multiple loads. They can create fault paths between appliances, defeating the purpose of isolation. So do not earth the secondary. The secondary should remain floating. Only local bonding between connected equipment is permitted. Inspect insulation and casing regularly. Isolation relies on good insulation and spacing. Damage can compromise your safety. Use only approved labeled isolating units. So portable isolation transformers must comply with this standard, AS/NZS 61558, and must be clearly marked isolating transformer. And overcurrent protection is still required. So fuses or circuit breakers must protect both windings against overload and short circuit. So there is a question in your assessments that some people have been getting incorrect due to lack of detail. This is basically kind of the list that you need to be referring to. It is in the SCORM packet for your reference as well. If you've gotten the question wrong, I have noted that when I've marked it. So why should we never connect more than one appliance to the same isolating transformer? Well, we've kind of talked about it. A fault in one could energize the metalwork on the other, reintroducing a shock hazard. So that's why we don't connect more than one appliance to the same isolating transformer. Unless they are designed to work in conjunction, like the vacuum cleaner having another appliance plugged into it, and that's how they work. Sorry, it's a bit of visual aid. So, yeah, the guy is getting a bit of a zap. The current has nowhere to go. So we're getting a zap from one appliance connected to one transformer. There is no earth reference. The current has nowhere to go. But if we were to plug 2 appliances in at once, there is a potential 230 volt shock between the 2. Cool. So a technician uses an isolation transformer to power a lamp in the damp maintenance area. If the lamp develops a fault that makes its casing live, what happens? So we have a technician using an isolated transformer to power a lamp in a damp maintenance area. If the lamp develops a fault that makes its casing live, what happens? Yeah. So theoretically and more than likely practically, nothing would happen. You would not receive a shock because there is no return path. What if there was another metal appliance connected at the same time? Yeah. So there is a potential of getting a shock because we have a return path from the lamp to the other appliance. There is a potential for a shock. Not a guaranteed, but there is a potential. That is the main thing we want to try and avoid. So, some key takeaway points. Isolating transformers transfer power magnetically, not electrically. They prevent shock current paths by keeping the secondary circuit floating. Only one appliance should be connected per transformer. Essential for safe working in damp, confined, or test environments. They're a great example of engineering safety by design. They don't rely on the user's reactions, they simply remove the danger in the first place. I'll give you guys a chance to at least get those notes down before we move on. And does anyone have any questions about isolating transformers? Okay, does anyone need more time or should we move on to the next section? Sure, sweet. Okay, good for everyone else. Sing out if you need more time. Cool. So now we'll talk a little bit about your instrument transformers, CTs and VTs. So we've talked about transformers that step voltages up or down for power and safety. Now we'll finish by looking at two special types, instrument transformers. So these don't power tools or lights. They're used for measurement, metering and protection in switchboards and substations. So some examples. So this is an example or a diagram for a current transformer. You see the primary current is a single conductor with a coil wrapped around a toroidal iron core, which outputs a readable current value. So basically the winding is our secondary, whereas the primary is one conductor in this example. And this is a type of potential transformer, a capacitor potential transformer. If you see here, it's connected to the high voltage supply at 2 points, and using capacitors and an intermediate transformer, we are then able to use a load to determine the voltage. So we use it to measure the voltage on the HV supply. Cool. So this is an example of the high voltage potential transformer. It's a cutaway with all the different parts labeled. And here we have an example of a high voltage current transformer. So these devices let us measure huge voltages and currents, or in the case of high voltage current, small currents, safely by scaling them down to manageable levels for instruments or relays. In the case of the one for the high voltage, it allows us to measure it safely without having to put a clamp meter on the high voltage line. Because I imagine the guys who work on the HV, you wouldn't want me climbing up and putting my little clamp meter around the high voltage wires. I might get a little bit, I don't think my meter could handle it. It's not designed to read currents on voltages that high. So first, we'll look at our current transformers. So our current transformers, or CTs. Some of you guys might be familiar with them, especially if you do any solar work or you work on any installations that are high current, like schools or industrial sites. So they're basically, they step high line current down to a safe measurable value, usually between 5 to 1 amps on the secondary. It operates on the same magnetic induction principle as any transformer. The primary winding is in series with the load, sometimes just a single heavy conductor passing through the core. In the case of if we're doing it to measure for our kilowatt hour meters or our power meters, it's wrapped around the mains conductor. The secondary winding has many, many more turns of fine wire connected to measuring instruments or protective relays. So for example, a CT with a ratio of 100 to 5 means that when the primary carries 100 amps, the secondary delivers 5 amps to the meter or the relay. So outside of a CT for measuring current for incoming supply, what kind of safety device might we use this for? Yeah, technically an RCBO uses one, or a kind of CT inside of them. But if we were using an external one, what might we use it for? So if the current flowing through a conductor into a device reaches a certain point, the secondary current will reach a certain point, which will trigger a safety relay, which could activate an alarm, or it could activate a fan to start a cooling process. It could start a water pump. There's all kinds of things. I've seen guys use a CT to turn on a laundry fan when the current flowing through the conductor to the power point of the washing machine reached over a certain value. So there are all kinds of different applications for a CT, for a current transformer. Cool. So some typical applications would be your switchboards and your main distribution panels, especially if the current flow is going to reach above 80 amps. Cool. So industrial meters, so kilowatt hour meters and demand meters. Obviously, if you've got current flowing into an industrial site, it's going to be many magnitudes higher than a residential installation. So your standard kilowatt hour meter cannot handle it. And believe it or not, unless you guys have seen them, they use the exact same meters that you use in domestic as they do in industrial. They just hook up CTs to the mains to more accurately monitor the current safely. Cool. So protection relays, so overcurrent, differential, or earth fault detection. If you put one around the earth conductor and it's calibrated correctly, it can send a warning or deactivate a contactor or the mains if there's too much current flowing in the earth conductor. Earth fault detection, obviously also your RCBOs and your RCDs. Cool. So the CT is designed to produce a precise current ratio at a particular burden. So maybe due to long cable runs or too many devices connected, the CT will produce a higher voltage to drive the current, the magnetic core will saturate, and its output will become inaccurate. So that's when metering or protected relays can start giving false readings. So we need to make sure the burden is accurate. So burden and accuracy, the definition. The burden of a CT is the load connected to its secondary circuit, including the impedance of meters, relays, and connecting leads. It is usually expressed in VA at a secondary at rated secondary current. So typical burden ratings, protection CTs can tolerate higher burdens. Metering CTs require tight accuracy. Again, we need to make sure that we don't increase the burden, therefore decreasing accuracy. So the typical burden ratings are 5 VA, 10 VA, or 15 VA, depending on CT size and purpose. So they come rated in VA. So we need to make sure that our burden is not going to be too high for the CT. Is this making sense? You can also think about burden as your impedance. That's the total impedance of the measuring circuit. Cool. So let's have a look at a practical example. So a CT is rated at 100 to 5 amps at 10 VA. The connected relay and circuit wiring imposes a total burden of 8 VA. This is acceptable. Accuracy will be maintained. But if another device on a longer cable with a higher impedance is added and the total burden rises to 16 VA, the CT output will distort and readings will no longer be accurate. So we'll look at calculating the CT burden. So we have a 105 amp CT rated at 10 VA. The wiring between the CT and the relay has a resistance of 0.15 ohms and the relay input impedance of 0.35 ohms. Cool. So first we calculate the total impedance. Cool. So the Z total is equal to 0.15 because that's the wiring between the CT and the relay. And then we have 0.35, which is our input impedance, which gives us a result of 0.50 or 0.5 ohms. So our second step is we calculate the actual burden. So burden is equal to I supply squared times impedance total. So that is our burden. So it's 5 squared times 0.5, which gives us 12.5 VA. So we compare that with our CT rating. It's only rated for 10 VA, but the connected burden is 12.5 VA. Therefore, it is overloaded. So the consequences of this. So it's the same thing. So the outcome, the CT will operate inaccurately. The ratio and phase errors will increase. The relay may under or over respond during a fault. And in severe cases, the CT core could overheat or saturate during normal load. So what are two ways we could reduce the burden on this CT? So how could we reduce the burden on this CT? Yep. We could use a VA rating, but what if we can't get another CT? What are some other options other than changing ratios or changing the VC? Yep, we could look at bigger wiring. Yep, we could up the cross section of the cable. The other thing we could do is we could shorten the wiring, because if we shorten the wiring, we decrease the resistance because there's less cable to flow through. Obviously, if that's not an option, we can use bigger wiring. Normally, the CTs or the measurement CTs we use in general work will come with leads attached, and they're matched to the CT to ensure it is not overburdened. Cool. So now we check if we have an acceptable burden. So we have a 200 to 5 amp CT rated at 15 VA, and it feeds a meter, 0.25 ohms, through 20 meters of 2.5 twin cable with a 0.14 total loop impedance. So the first thing we're going to do is check our Z total. So 0.39 ohms, 0.25 plus 0.14. We're going to figure out the burden, 5 squared times 0.39, 9.75 VA. So it is acceptable because it is below the 15 VA rating. So our accuracy will be maintained. So always compare your calculated burden against the CT's nameplate rating. Staying below that limit means your measurements and protection systems remain accurate and the CT won't be stressed magnetically. Cool. So some safety notes. Never open circuit the secondary while the primary is energized. If the secondary is disconnected, there's no opposing magnetizing current. The core saturates and dangerously high voltages, hundreds of thousands of volts, can be induced, especially if we're on a high voltage side. Cool. So the risk is electric shock, flashover, or insulation failure. Always short circuit or load the secondary when not in use. The standard CT shorting links are fitted for this. We must ensure correct polarity for protection relays. Terminals are usually marked P1, P2, and S1, S2. All making sense? Anyone got any questions? Cool. So, some operating principles. So, if the secondary current is 5 amps and the CT ratio is 200 to 5, what is the primary current? So for the current transformer, the secondary current is 5 amps and the CT ratio is 200 to 5. What's our primary current? Yeah, so I primary 200 divided by 5 times 5. Basically, the 5s cancel each other out, and we're left with 200 amps. Pretty straightforward. Now we'll move on to voltage transformers. So they're known as VTs or PTs. So they can be called voltage transformers or potential transformers. And remember, when we're talking about voltage, we're just talking about potential difference, which is why we have potential transformers. So the purpose and principle. So a voltage transformer steps down high voltage to a standard safe value, usually about 110 volts. They operate on the same principle as a power transformer or a current transformer, but is designed for high accuracy and low loading. The primary is connected in parallel with the supply. The secondary feeds meters or protection relays. So for example, an 11,000 to 110 volt VT has a ratio of 100 to 1. So if the meter reads 110 volts, the actual system voltage is 11,000 volts. So it's just basically a straight transformer. We're just checking the voltage. And we're only worried about the voltage. We're not measuring current at this stage with this transformer. Cool. So our applications for these. So high and medium voltage switchgear. So voltage switchgear that falls outside of the range of standard voltages. So it can be used for industrial and commercial metering panels. And the voltage sensing for automatic protection or control equipment. So we're checking to make sure the voltage is exactly where it's supposed to be, that we're not getting under voltage or over voltage. And if that happens, it will activate protection relays, switching out circuits. Any of the guys who work on the HP side, do you guys work with the voltage transformers at all? Every week? You've only rewired them? Oh, yeah, courses on them next year? Sweet. I was gonna say, Troy, are they like the massive ones or are they kind of like benchtop ones? Sort of. What size are we talking? Almost massive. Okay. So yeah, for the most part, if you're kind of the average electrician, most of the time won't come across too many VTs or PTs. I don't think, yeah, no, I have never worked on any of them. So it is kind of a specialized measurement type of device. Cool. The safety and installation notes. Always fuse both the primary and the secondary circuits. Each one side of the secondary, earth one side of the secondary to prevent floating voltages. The VTs must maintain accurate ratio and phase angle under normal loading. Therefore, they're lightly loaded by instruments only. Oh, so why do we fuse both sides of a voltage transformer? So why do we fuse both the primary and the secondary? Well, we fuse anything for safety reasons, but why in particular are we fusing both sides of the transformer? It's part of it. Okay. So the reason we fuse both sides is to protect against faults on either winding and to prevent feedback from the secondary to the high voltage system and to protect the um, low voltage from the high voltage side. So we protect the metering equipment from the high voltage side and we're protecting the high voltage from being having feedback from the secondary onto the high voltage side. Okay, so CTs and VTs are the eyes and ears of the electrical system. They let us see what's really happening without having to touch dangerous voltages or currents. So treat them with respect, especially the CT secondaries, and they'll work quietly in the background for decades to come. Cool. So which transformer type do you think is most critical to get right for safety? All right, so Tim says isolating. Any advances on that? So most people are going isolating. But what about a CT that is connected to a protection circuit? Or a voltage transformer inside of a high voltage switchyard? Yes, isolating transformers protect one or two people or an area, but CTs and voltage transformers can be quite important to get right as well. You can make a case for any of them being critical to get right for safety, but if we're talking about protecting people who are the most vulnerable, more than likely isolating. So why might a transformer fail even if its ratings are correct? What can be some readings that it fails even if its ratings are correct? Age, wear and tear, yep. Block ventilation, age. Vibration, yep. Incorrect installation, definitely. Yep, lack of maintenance. High surges, internal arcing, yep, so like a manufacturing fault. Out of sync, yep. What do you mean by out of sync, Troy? Please expand on your answer. Okay. I thought you were possibly talking about incorrect frequency. Oh, yeah. Cool. So what would you check on a transformer nameplate before installing it in a damp area? Yep, that would be the first thing we would check. It's IPP rating. Cool. So cool. So that wraps up our study of transformers as far as the night class goes. So we talked about their construction and operating, all the way through to their use for protection and safety. So next session, we'll be looking at using the same kind of analytical thinking into the next component of electrical systems and design, which I believe is capacitance, inductance, and electronics. Let me just check the Learning Hive. But yeah, that is our lesson as far as that goes. Hold on.